Hello, uh, welcome again. Today I'm going to read about SSIM, which is structure or structural similarity index measure. It is a metric which is basically used in image processing. Uh, let's read it now. The structure, the structural Similarity Index Measure (SSIM) is a method for predicting the perceived quality of digital television and cinematic picture as well as other kind of digital images and video. It is simply a predict metric used to check or measure the human quality based on human perception. It is also used for measuring the similarity between the two images. The SSIM is a full reference metric. In other words, measurement or prediction of the image quality is based on the initial uncompressed or distortion pre-images as a reference. Measure the similarity between the two images, and it has the full formula, it has the full algorithm on how it measures the similarity between the two images. SSIM is a perception based model that considers the image degradation as a perceived changes in the structural information while also incorporating the important perceptual phenomena including both luminance masking and the contrast masking. This distinguishes from other techniques such as MSE, mean squared error, or peak signal to noise ratio that instead estimate the absolute errors. SSIM is quite different from MSE or PSNR. MSE measures the pixel level difference between the target and the given image, whereas MSE measures the similarity, structural similarity between the two images rather than the pixel level similarity. Structural information is the idea that pixels have strong independence, especially when they are spatially close. This dependencies carries the important information about the structure of the object in the visual space. Luminance masking is a phenomena whereby the image distortion in this context tends to be less visible in the bright region, while contrast masking is a phenomena whereby distortion becomes less visible where there is a significant activity or texture in the image. Luminance masking is a phenomena whereby the image distortion tends to be less visible in the bright context, yeah, bright region, and for the contrast masking, the distortion becomes less visible where there is significant activity or significant texture in the image. Let's read about the history. The predecessor of SSIM was Universal Quality Index, or Wang Bobik Index, which was developed by Zhou Wang and Alan Bobik in 2001. This evolved through their collaboration with the Hamid Sheikh and Iro Simonsel into the current version of SSIM, which was published in 2004 in IEEE Transaction on Image Processing. In addition to defining the SSIM quality index, the paper also provides the general context for developing and evaluating the perceptual quality measure, including connection to the human visual, neurobiological, and perception, and direct validation of the index against human subject rating. The basic model was developed in the laboratory of for image and video engineering at the University of Texas at Austin and further developed jointly with the laboratory of for computational vision at New York University. Further variants of the model have been developed in the image and visual computing laboratory at University of Waterloo and have been commercially marketed. SSIM subsequently found the strong adoption in the image processing community and the in television and social media industry. The 2004 SSIM paper have been cited 5,000 times according to the Google Scholar, making it one of the highest cited paper in the image processing and video engineering fields. It was recognized with the IEEE Signal Processing Society Best Paper Award for 2009. It also received the IEEE Signal Processing Society Sustained Impact Award for 2016, indicative of the paper having the unusually high impact for at least 10 following year from its publication. Because of its high adaptation by the television industry, the author of the original SSIM paper is accorded with the Primetime Engineering Emmy Award in 2015 by Television Academy. Let's go to the algorithm. The SSIM index is calculated between the two windows of the pixel value x and y of the common size from the corresponding location in the two images to be compared. These SSIM values can be aggregated across the full images by averaging other variation. In one simple cases, the further explained in the next section, the SSIM measured between the x and y is x is one image, y is another image, quarterly shifted to x, and the y is the target image with which is being compared to the axis. The formula is 2 mu x mu y plus c1 to mu xy plus c2 whole divided by mu x square plus mu y square plus c1 multiply to mu x square plus mu y square plus c2, and where mu x is the pixel sample mean of the x, mu y is the pixel sample mean of the y. Similarly, what is this? Alpha? Nah. Sigma. Now, sigma square is the sample variance of the x. Sigma y square is the sample variance of the y. Sigma xy is the sample covariance of the xy. And c1 and c2 are the two variable constants variable to stabilize the division with the weak denominator, which is given by the k1 l square whole square and c2 is equals to k2 l whole square, where L is the dynamic range of the pixel, means based on the how many bits are used to represent the one pixel, it is changing, which is typically 2 power number of bits per second per pixel minus 1. Typically, when we use the numpy, the default is the 8-bit. We use the 8-bit, but for high quality display and for working with the in animation or any studio, to get the high quality of high range of the color space, there can be 16-bit per pixel, 32-bit per pixel, depending upon the quality of the work you are doing it. The dynamic range can be changed. K1 is typically 0.01 and K2 is typically 0.03 by default. General formula and component. The SSIM formula is based on the three comparison measurements between the sample x and y: luminance, contrast, and the structure. The three comparison functions are LXY, means luminance, calculation of the luminance. It is using the 2 mu x mu y plus c1 divided by mu x square plus mu y square plus c1. CXY means the given the construct contrast component, which is given by 2 sigma x sigma y plus c2 divided by sigma x square plus sigma y square plus c2. It is the standard deviation. Sigma x is no variance, yeah, variance, and sigma x is the standard deviation. Yeah, xy is equals to sigma xy plus c3 divided by sigma x sigma y plus c3, and typically c3 is equals to c2 divided c2 is equals to cu1 divided by 2, and when we do all the things, SSIM is calculated by multiplying these all the component above component, and there is weighted component. There can be weighted component, but typically by default we use the alpha, beta and gamma is equals to 1. So we multiply all the component from the luminescence, contrast and structural component, and we choosing the third denominator establishing constant as the c3 is equals to c2 divided by 2. We get the exactly same formula as above. Leads to the simplification when combining the c and s component with the exponent beta is equal to gamma, as the number of c is then twice the denominator of s, leading to the cancellation, leaving just 2. Setting the weighted alpha, gamma, beta to 1, the formula can be reduced to the special case. So now this is the special case, and most of the simple cases which is used which can be used as default cases. Yeah. Mathematical properties. SSIM satisfy the identity of indiscernibles and symmetry properties, but not the triangular inequality or non-negativity, and thus is not distance function. However, under certain conditions, SSIM may be converted to the normalized root MSE measure, which is the distance function. Oh, I didn't know that. The square of such function is not convex but locally convex or quasi-convex, making SSIM a physical target for optimization. Oh. Okay, application of the formula. In order to evaluate the image quality, this formula is usually applied only on luma, although it may be applied on the color, example RGB value or chromatic YB, YCR. The resultant SSIM index is the decimal value between the -1 to 1, where 1 indicates the perfect similarity, 0 indicates the no similarity, and -1 indicates the perfect anti-correlation. For image, it is typically calculated using the sliding Gaussian window of 11 cross 11 or block size of window 8 cross 8. This window can be displayed pixel by pixel on the image to create the SSIM quality map of the image. In the case of video assessment, the author proposed to use the subgroup of the possible windows to reduce the complexity of the calculation. Variance, multi-scale SSIM. The more advanced form of SSIM, called multi-scale SSIM, it is conducted over the multiple scales through the process of multiple stages of subsampling, reminiscent of the multi-scale processing in the early vision system. It has shown to perform the quite well or better than SSIM on the different subject image and video database. Multi-component SSIM. Three-component SSIM is the form of SSIM that takes in account the fact that human eye can see difference more precisely on textured or in is region than on the smooth region. The resulting metric is calculated as the weighted average of the SSIM for the three categories of the region: edges, texture, and smooth region. The purpose weighting is 0.5 for edges, 0.25 for texture, and smooth region. The author mentioned the 100 weighting, ignoring anything else, but edge distortion leads to the result that is closer to the subjective rating. This suggests that is originally dominant role in the image quality perception. The author of 3 SSIM have extended the model into the full component SSIM. The edges type are further divided into preserved and changed edges by distortion status. The purpose weight is 0.525 for all 4 components. Structural dissimilarity. Structural dissimilarity may be derived from the SSIM, though it does not constitute a distance function, as a triangle inequality is not necessarily satisfied. DSSIM x y is given by the 1 minus SSIM divided by 2. Video quality metric and temporal variant. It is worth noting that original version SSIM was designed to measure the quality of the still images. It does not contain any parameter that directly related to the temporal effect of the human perception and human judgment. A common practice is to calculate the average SSIM of over all the frame in the video sequence. However, several temporal variants of the SSIM have been developed. Complex wavelength SSIM. The complex wavelength transform variant of the SSIM CW SSIM complex wavelength SSIM is designed to deal with the issue of image scaling, translation, and rotation. Instead of giving the low score to the images with such coordination, CW SSIM take advantage of the complex wavelength transforms and therefore yield the higher score to said images. Thus, CW SSIM is defined as, this is the formula, 2 CXI plus K and squaring of component. I think this and our formula are quite different. Okay, where Cx is the complex wavelength transforms of the signal X and Cy is the complex wavelength transform of the Y. Additionally, K is the small positive number used for the purpose of function stability. K is for the function stability. Ideally, it should be 0. Like SSIM, CWSSIM has a maximum value of 1. The maximum value of 1 indicates that two signals are perfectly structurally similar, while the value 0 indicates no structural similarity. SSIM plus index is based on the SSIM and is commercially available tool. It extends the SSIM capabilities mainly to target video application. It provides the scores in the range of 0 to 100, linearly matched to the human subjective rating. It also allows the adapting the scores to the intended viewing devices, comparing video across different resolution and contents. According to the author, SSIM Plus achieves higher accuracy and higher speed than other image and video quality metric. However, no independent evaluation of the SSIM Plus has been performed, as the algorithm itself is not publicly available. Okay, see SSIM. In order to further investigate the discrete SSIM from theoretical perspective, the continuous SSIM (CSSIM) has been introduced and studied in the context of radial basis function interpolation. SSIM ULA-CRA and SSIM ULA-CRA2 are the variant of SSIM developed by the Cloudinary with the goal of fitted subjective opinion data. The variant operate on XYB color space and combine the YAMS SSIM with the two type of asymmetric error maps for blocking, ringing, and smoothing blur common compression artifacts. SSIM ULA-CRA2 is the part of LibJXL, the reference implementation of JPEG-XL. Other simple modification: the R star correlation matrix is based based on the variance metric of the SSIM. It is defined as R star x by y is given by the covariance of x and y divided by the uh, sigma x and sigma y, where sigma x sigma y is not equals to 0 or 1 when both standard deviation are 0. It's not equals to 0. 1, it is 1 when both standard deviation are 0, and 0 when 1 is 0. It is found it has found use in analyzing human response to the contrast detail phantoms. SSIM has been used in gradient of images, making GSSIM is especially useful on a blurred image. The modification above can be combined. For example, 4GR star is a combination of 4 SSIM, GSSIM and R star. It is able to reflect the radiologist's preference for the images much better than the SSIM tested other SSIM tested variants. Yeah. Application: SSIM has application in variety of different problems. Some problems are image compression. In lossy image compression, information is deliberately discarded to decrease the storage space of the images and video. The MSE is typically used in such compression scheme. According to the author, using SSIM instead of MSE is suggested to produce the better result for decompressed images. Image restoration focus on solving the problem y is equals to x plus n, where y is the blurry image that should be restored, x is the blur kernel, n is the additive noise. X is the original image we wish to recover. The traditional filter which is used to solve this problem is Wiener filter. However, the Wiener filter design is based on MSE using SSIM variant. Especially SAT-SSIM is claimed to produce the better result according to the algorithm author. Pattern recognition: since SSIM mimics the aspect of human perception, it could be used for recognizing the patterns. When faced with the issue of image scaling, translation, rotation, the algorithm author claims that it is better to use CWSSIM, which is insensitive to this variance and may be used directly applied by the template matching without using any training sample. Since data-driven pattern recognition approaches may produce better performance when a large amount of data is available for training, the author suggests using the CWSSIM in data-driven approaches. Performance comparison: due to the popularity, SSIM is often compared to the other metric, including the more simple metrics such as MSE, PSNR, and other perceptual images and video quality metric. SSIM has been repeatedly shown to significantly outperform MSE and its derivative in the accuracy, including the research by its own author and other. A paper by Salman and Young claims that the performance of SSIM is much closer to the MSE than they usually assume. While they do not dispute the advantages of SSIM over MSE, they state that analytical and functional dependency between the two metrics. According to the research, SSIM has been found to correlate as well as MSE-based methods on the subjective database other than the database from the SSIM creator. As example, they cite the Rybeman and Pole, who found that the MSE outperformed the SSIM on the database containing the packet loss impaired behavior. In another paper, analytical link between PSNR and SSIM was identified. Okay, this is for today, and I didn't know. I only got to know SSIM when I was looking through a notebook for deep learning, where it has used the concept of SSIM. At that time, I didn't know how what this metric is about, and I get fascinated, and it is quite fascinating metrics. But when the pixel similarity is 1, it does not guarantee the pixel level accuracy between the image and the target images. For that, the MSE loss gives the pixel level error between the two images. But SSIM is good when we want to know the generated image is good by the standard of human preference rather than the unreliable metric like MSE, which quite be pretty hard because the upper bound is large and same image having the same MSE can have the different noise, different blurring effect, and it will be in different from the human perception also, and it is quite good concept, I think. Okay, this is for today, and see you next time. Thank you.